Before we talk about electric forces, I want to talk about electrostatic equilibrium. We've talked about how charges, electrons, can change from one object to another. Well, we should note that when a charge is placed on a conductor or an object, it will very quickly distribute itself over the conductor's surface. This happens extremely quickly, um, and and almost immediately these charges, they'll be distributed and they will be at rest in what's called static equilibrium or electrostatic equilibrium. Static means it's at rest. We talked about how two like charges, like positive and positive, will push away from each other, and two opposite charges, like positive and negative, will push towards each other. But how do we identify the value of the forces between two charged objects? To do that, we're going to use Coulomb's law. Coulomb's law lets us determine the forces between two charged particles. Coulomb's law applies to point particles. This is the equation for Coulomb's law from your AP Physics 2 equation sheet. It says the magnitude of a force, an electric force, or the force between particles, which is measured in newtons, is equal to 1 over 4 pi epsilon naught. And epsilon naught is called vacuum permittivity. It's this value. This value is on your equation sheet, so you don't need to learn it. You just need to know that this is a constant. This is multiplied by the magnitude of charge 1 times charge 2. So if you have two charges, you multiply them together, you get the magnitude, and that's going to go into the equation. And that is divided by r squared. R is the distance between the center of the two particles that we're looking at the force between. We can also shorten 1 over 4 pi epsilon naught to be the variable k, and k is just Coulomb's law constant. This is the same value, it's just written two different ways. It's written as 1 over 4 pi epsilon naught on your equation sheet, so you should be familiar with that. But when you're doing the math, you can replace this with the shorter value of 9 times 10 to the 9th Newton meters squared per Coulomb squared. Notice that our charges are given in coulombs, radius is given in meters, and it gives us a force in newtons. So this equation looks a little bit similar to another equation that you saw last year, and that is the force of gravity. Force of gravity also has mass 1 times mass 2, while this has charge 1 times charge 2, and it has over r squared. And if you remember, with gravity, as you move away from the object, your force decreases geometrically. The force between two charged objects is a long-range force, like gravity. As the distance increases, the force decreases, but not just by a factor of 1 over r, by a factor of 1 over r squared. So let's look at an example using this equation and also this equation. Let's say we have a small positive charge called q dot placed at the black dot, and we have 4 different examples where q dot is placed at 4 different locations. In which case is the force on the black dot the largest, and in which case is the force on the black dot the smallest? We need to solve for the force for each of these and then make a comparison. So at A, the force on this dot is going to be equal to k, we're replacing 1 over 4 pi epsilon naught with k, times the charge at the plus, which is q, times q dot over the radius between them squared, which is just r squared. So this is going to be the force here. Now this is the force on q dot. It is also the same force on this point. Just like gravity, the forces are equal and opposite. So if you find the force on one point, you've also found the force on the other point. For B, the force on the dot is going to be k times this charge, which is 2q, times this charge, which is q dot, over the radius squared. So it's over 4r squared, because the 2 had to be squared. So we have a 2 on the top and a 4 on the bottom. We can simplify this. We can pull out the 2 and 4 and make it 1/2 times q dot over r squared. On C, we have 2q as our charge, and r is our radius. So we get k times 2q times q dot over r squared, and then pull out the 2, and we get this as our force on the dot. Finally, for D, our charge and q dot are both just q dot, and the radius is 2r, so it has to be 4r squared on the bottom. We pull out that 4 and we get 1/4 q dot over r squared. So looking at these four forces, which is the largest? The answer is C. And in which case is the force on the black dot the smallest? Because D is 1/4, has a 1/4 factor, D will be the smallest force. That was looking at two charges interacting with each other. But you could have multiple charges all affecting each other. The force felt by one particle is going to be the sum of all of the forces around it. We looked at this last year when we did static equilibrium, where we had multiple forces like friction, applied force, tension, normal force, gravity, and the net force is the sum of the forces. So it's the same with electric forces. Forces are vectors, so you may have to separate them into x and y components. For the example in this video, we're just going to use the x direction, but in class we will do x and y components. So net force on an object is going to be the force of 1 on the object plus the force of 2 on the object plus the force of 3 on the object. So let's look at an example. Let's say we want to find the force on A from all the forces around it. The force on A is going to equal the force of B on A plus the force of C on A. So let's solve this problem. What is the magnitude and direction of the electric force on charge A? Well, first let's look at the direction that these forces are going to act, because we're doing a sum of vectors and we need to know the direction of those force vectors. For B on A, the force of B on A, B and A are opposite charges, so they're going to attract each other. So the force of B on A is to pull A to the right towards B. The force of C on A, since they are like charges, A is going to be repelled by the charge at C. So the force of C on A is going to be to push A away. So we have these two forces to consider. First, let's calculate the force on A. Let's see that the sum is going to be the magnitude of the force of B on A, and we're going to subtract the force of C on A, and that has to do with the sign of those charges. So the overall force will be whatever the force of B is plus the minus of the force of C on A. To get the force of B on A, we're going to do K, which is 1 over 4 pi epsilon naught, which is 9 times 10 to the 9th Newton meter squared per coulomb squared, times the magnitude of the charge B times the charge A. The charge B is -1 nanocoulombs, and a nanocoulomb is 10 to the -9th coulombs. So -1 nanocoulombs is -1 times 10 to the -9th coulombs. The charge of A is 1 nanocoulomb, so it's 1 times 10 to the -9th coulombs. The magnitude of those charges together divided by the radius squared, and the radius between the two is 1 centimeter, which is 1 times 10 to the -2 meters, and then squared. When we multiply it out, this negative is going to be eliminated because it is the magnitude. So we end up with just the value, which is 9 times 10 to the -5th newtons. For the force of C on A, we're going to have K times the charge of C, which is positive, times, this is actually switched. This is going to be the charge of A, which is positive, the charge of C, which is 4 nanocoulombs, 4 times 10 to the -9th coulombs, divided by the radius. And in this case, the radius from A to C is 1 plus 1 centimeter, so it's 2 times 10 to the -2 meters squared. When we solve this, we just multiply everything together, and we get the force of C on A is 9 times 10 to the -5th newtons. To get the overall force on charge A, we're going to plug these new values into this equation. The force of B on A minus the force of C on A, so that's 9 times 10 to the -5th minus 9 times 10 to the -5th, and we get an overall net force of 0 newtons.